Today we go for another new topic which is termed as digital control system. Now, first of all, the first topic which we have covered in this control system second was of that of state variable analysis. We have highlighted the drawbacks of conventional control system, that is transfer function approach, and then we have shifted towards the state variable analysis method. And now we are shifting towards another system under the category of control system, the digital control system. Before proceeding it, that is in the sense proceeding towards the analysis parts, first of all we will highlight the advantage, that why we are going for digital control system, why we are unhappy with the analog control system. First of all, that should be highlighted, and then we will go for the digital control system analysis. So why we are going for digital control system? When the things were okay, are we not satisfied with the analog system? What is the opposite of digital? Analog. Analog means the system, the signal is continuous. The signal is continuous, and if discontinuity is there, then it should be periodic. This is the definition of an analog system. But when things in our practical world also, every input is analog, then why we are going for digital system? For example, this fan is there, okay? What type of signal you are providing? An AC waveform, a continuous AC waveform. It is not that you are giving in the form of binary numbers. Is it? You are giving in the analog form, okay? Then why we are going for digital system? Okay, when things are, the input is analog, output is analog, then why in between the digital has been introduced? What is our advantage? The main advantage is that the digital system is being basically used for control purpose. It is being used for control purpose, okay, and it is a mediocre. It is neither your input nor your output in most of the cases. It is your mediocre. That is, it helps in the processing. How? How? Through which media? Through computer. Is it clear? Through computer. Now computer has what advantage? Those advantages which computer has are the advantage of this digital control system. Because how you will do the processing? With the help of computer. And computer has what? A processor. A processor made up of chips. Transistor, diodes, chips and all this. Is it clear? And what versatility this processor has? High memory storage. Is it clear? At present, you have a computer of 1 and 2 TB. Is it clear? Do you agree or not? So, you can store the data. As the time is passing, as the new generation is coming, the processing speed is fast. A time was there when you were purchasing the desktop computer, it was having a frequency of 1.8 megahertz, but now it is 2.3, 2.4 gigahertz. Is it not? Okay, so likewise, what this gigahertz is representing? This is representing the processing speed, means that much of calculation can be done within few seconds. 2.8 giga calculation per second can be done by that processor. Is it clear? So, speed, okay, storing of data, is it not? Reliability, your data will remain for last and long. Is it clear? If you tell to a human, if I ask you about the state variable solution, you have forgotten. Just 1 month has passed. But in case of the computer storage, you can keep it for years. Is it clear? And it can be done in a single small piece of thing, computer. Less space is required. And day by day it is economical also. Is it clear? So reliability is also there. And most important, flexibility. Most important, flexibility in the sense, suppose you have made a program that you take the input this, process it, apply P, this much of gain, this much of proportional gain, this much of integral gain, this much of derivative gain, and give me the output. So what happens? Input will come converted into digital form, processed through that software. Again, it will give a digital form output converted into analog, and you will get the output. Now you want, no, I want to change the Kp, Ki and Kd. What you have to do? You have to go only through software. In software, change the value of, or make it user friendly. It will ask every time how much Kp you want to add, how much Ki you want to add, how much Kd you want to add. Just insert the value through keyboard, okay? It will accept it, and it accordingly it will set it, and you will get the desired output. Is it not a flexibility? Is it a flexibility or not? Okay, so these all, and accuracy, speed, accuracy, fastness, flexibility, high memory storage, okay, these all features make us to move towards a digital control system. Practically all systems are analog. Your input is analog. Suppose a plant is running, suppose Hindustan Zinc is there, okay, what in the plant? It will give motor what? Supply. Okay, suppose a blender is there, or a crusher is there. Okay, crusher, what is there? What is there in crusher? When I say crusher, name is meant for crushing, but what actually is there? A motor. To this motor, a blade has been connected. So when you give supply to that motor, okay, the motor will rotate, and the blade will also rotate, and whatever material is present nearby that blade, it will cut it and crush it. It is rotating at such a high speed that within a few seconds or within few minutes, the material, that is limestone or whatever is being put, raw material is being crushed. Is it clear? That is why it is known as crusher. And basic part is what? Motor. So what supply you are giving? Are you giving binary numbers? No, I will make 230 binary, convert it into binary number. Now I will give 1, 0, 0, 0. Are you giving like this? No. What you do? You switch on. Conventional electricity will pass through the wire, give it to the motor, motor will run. Okay. But now what happens? Suppose I want that motor should run at a particular speed. Motor should run at a particular speed, and for that purpose my input I am giving a voltage. Okay. Now I will set it. So I will set, I want 1000 RPM. How much? 1000 RPM. So I will insert the data. Okay. What will happen? It will take the input supply. Clear? And now it will convert into digital form. Because of this advantage, processing is fast. It will immediately take. Now in my saying and describing all this, it takes a seconds, minutes. But these all things happens practically in a milliseconds, microseconds. Is it clear? It will take the input, convert into binary form, okay, and then go to the controller. Controller says this is the input. He wants this much output, 1000 RPM. Okay, so he will accordingly find out what is the voltage is required. So he will give it to the chopper or whatever it is, okay, to converter. The converter will reduce the voltage, again convert it into analog input and give it to the motor. And motor will start running at 1000, and this being a closed loop system, it will go on till it does not reaches 1000 RPM. Now all this process happens within a microseconds. The gigahertz frequency representing that things are going on in nanoseconds. What is the opposite of giga? 10 to the power minus 9. Nano, is it not? So things are happening in a nanoseconds. You got my point? Okay. And again the motor will run at 1000 RPM. Previously the same thing was what there? Okay. You want 1000 RPM. You will put an speedometer, okay, and now you will manually try to increase it till it does not reaches the 1000 RPM. Is it clear? Or if it is analog input is there, that analog input will be fed. You will just there was used to be a program, okay, 1000 RPM is there, so accordingly it will choose from program what alpha is required. Okay, so alpha is being fired. Converter will give only that much of voltage. But now what happens? You are converting the whole thing into digital. Is it clear? And getting the output only in analog form only. Only in between processing is going in a digital form. So looking to this advantage, we will go for digital control system. Is it clear or not? So in your university exam, you can be asked, highlight the advantage of digital control system. Is it clear or not? Okay, you can highlight that speed, accuracy, high memory storage. Is it clear? Then flexibility, and what else? Any more from your side? Yes, that is speed we have already covered. Accuracy, speed, flexibility, and all these are the advantage of the digital control system. Now let us begin with the first important technical term of digital control system. Okay, first it was not digital, it was arise as a sampling. The first term comes what? Sampling. Now we will discuss what is sampling. No doubt digital means converting into binary form. When I say digital, it means binary form, that is 1 and 0. You are expressing all the numerical data into 1 and 0 form. Is it clear? But now, before going for digital, I will introduce to you about the sampling. What is sampling? What do you mean by sample? Now what happens that suppose a company is manufacturing certain things. 1 lakh a particular product is being manufactured by a company. Now what happens, you might have seen on the most of the products some specialized labeled is there. For example, in case of electrical appliances, ISI. In case of food like jam, bread, butter, FSSAI, food security and something this is there. Is it clear? Okay, what these companies, these are the standard companies developed by the government in order to provide a certification that your product is according to the standard. Your product is according to the standard. Suppose a company is developing 1000 sauce bottles. So not 1 lakh sauce bottles. Okay, so will it send all its 1 lakh bottles to that standard bureau? For example, it is sending to the FSAI. Okay, will it send all 1 lakh bottles to the FSAI? It will send some samples. Okay, so this is produced on this month. This is produced this 1000, this 500 bottles of this month, this 500 bottles of this month, this 500 bottles of this month. Suppose in all they have sent 2000. How much? 2000. Now they will test these 2000 bottles, and accordingly they will mark, yes, the quality is according to the standard or not, or at par or not. Is it clear? And they will put a label on it. Yes, it satisfied our standards regarding the food and security. Is it clear or not? Okay. Similarly, a tubelight manufacturer is there like Philips. Okay, the whole production is there near about 1 lakh per day. Okay, so will it send all 1 lakh tube lights? It will sell the particular samples. Okay, 1000 samples is being sent to the ISI. ISI will check whether this much luminance is there, whether it is sustaining this much of over voltage or not. Okay, what is the quality of the coil, what is the quality of the, that is the choke, what is the quality of this glass material, okay, of what flow, what is the quality of the fluorescence material, okay, what are the material of the connecting metals. Is it clear? So everything after being checked for 1000 sample, it give a certification. Yes, now you can put ISI label on every product. The same concept has been borrowed in the control system also. Okay, they says that you have a continuous signal. They says that you have a continuous signal, then instead of giving the continuous signal, why not we take samples of the signal? Why not we take the samples of the signal? For example, suppose this is voltage signal is there and this is your time axis, a signal, arbitrary signal is there. Okay, I take this, then 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 I take this, like this way. So what I am doing? Rather than taking the complete signal, I am taking the sample of the signal. I am taking the sample of the signal at different times. Okay, let this time be T1, T2, T3, T4, T5, T6, T7, T8, T9 and so on. Okay, so what happens? I have taken the samples of my signal at different times, and now these samples are being used for the further processing purpose. Okay, so from it is clear what is meant by sampling. Is it clear? I have taken the samples of the signal and fed it to the system, okay, for further processing. This process is called sampling process. This process is called sampling process. So what will be my output? Now what happens? How to I have just shown a single line, but practically what happens? I have to give a pulse. What I have to give a pulse? Though I have shown what? Impulse. I have shown what? Impulse. There are two words, pulse and impulse. You might have learned in circuit theory. Is it clear? Pulse means a waveform of particular duration. By impulse means exists at only t is equal to 0 and for other time it is 0. Is it clear? So basically what happens when I am applying a pulse? Like this. Is it clear or not? Okay, so what will be my output? When I apply, actually basically you can imagine like this. This is a continuous signal. This is my time axis. Okay, now I am applying what happens? Pulse of equal amplitude and duration is being applied to this continuous signal. So what will happen? Suppose, clear? Okay, then so my output will be like this. Is it clear or not? This will be my output. Now I will be using this sample for further processing. This process is called sampling. Is it clear? This process is called sampling. Now what is the advantage of this sampling? Why I am going for this sampling process? Because from your point of view, from when you draw any signal on a blackboard or on your copy, then you simply draw a one period waveform. Is it not? But actually it is what? It is continuously moving. Okay, so for processing using the continuous data, we are taking certain samples. Okay, and that samples is being further utilized in control applications. Because ultimately once we get the idea about the signal, why to fed every time the continuous signal? Please understand these things. Is it clear? This all sampling is meant for control. Is meant for control. We have to control our system. Why we are controlling our system? Why we are controlling our system? In order to get the desired output for a given input. This is the basic aim of any control system. Okay. Now, in order we are giving input, definitely it will give some output. But we are not satisfied with our output. We want that for this input, this should be the output. And if I am not getting the output, what I will do? I will apply some control mechanism. Okay, and for control mechanism, I must get the idea about what is the input. So rather than feeding it the continuous input, the whole input, I am taking its samples. Take its samples, okay, and then feed it to the control mechanism. Okay, it will process it. Okay, this is your input. Okay, then I should increase this gain, so that you get the desired output. You are giving suppose input to this fan to obtain a particular speed. Okay, it doesn't mean that to the control mechanism you give the same input again and again. Means you are giving how much input to 30 volt. Okay, so it doesn't mean for control mechanism in order to obtain 1000 output you give in 230 volt. You take its samples. Okay, so this is how my input looks like. Its amplitude is maximum this much, and this is how it looks like. Now process it. Find out what should be the value of Kd, Kp and Ki in order to obtain the 1000 RPM speed. So it will say, oh, this is the input, this is the amplitude, it should be the Kd, Ki and Kp from the software, and adjust it, and accordingly it will adjust the Kp, Ki, Id, and you get the ultimately 1000 RPM speed. This is the main objective of sampling. Is it clear that we have sampled the signal? Is it clear? Now what happens? This signal is to be recovered also. You got my point or not? Okay, this signal is to be recovered also. Okay, because now you have broken into samples. So the sample signal should again be converted into original analog signal. So will it be possible? Will this reverse engineering is possible? If I add sugar to milk and stir it, and then after few minutes I say, now take out sugar from the milk, is it possible? If I add salt to water with some lemon drops in it, okay, squeeze the lemon drop, add some salt in a water, and then stir it, and then I say take out that lemon drops and salt from the water, is it possible? These are irreversible phenomena. Okay, but here we again want my signal. I don't want that my signal should be lost. I want to recover my signal. Once it has been used for processing, give it back to me. Is it clear? You have just shared it. Yes, you want to control my system. Okay, take it for rent. And when you process it, you understand it, what is Kp, Ki, Id. Okay, give it back to me. That is, I have to recover my signal. Is it? So, is it possible to recover it? Yes, it is possible. Mathematically it is possible, and for that purpose there is a scientist known as Shannon. What is the name of that scientist? Shannon. Shannon has given its theorem which is known as Shannon sampling theorem. What is known as Shannon sampling theorem? Okay, that is very important and is used to be asked in the examination also. Okay, and sometimes what happens in examination, you will be asked what is Shannon theorem. Okay, you can directly write down. But in competitive exams, you will be asked what? You will be asked a system, I want to recover a signal having maximum frequency A, what should be the minimum frequency of the sampling? They will never ask. Competitive exam will never ask you direct question, what is Shannon sampling theorem? They will make a numerical question. Okay, they give a circuit diagram. The signal fed to this system is operating at 5 kilohertz maximum frequency. It is undergone sampling process. To recover the signal, the minimum frequency should be, the minimum sampling frequency should be. Now you say, sir, these data are vague. Nothing is being given. No R, no L, no LC. How I can find out it? No, you can find out with the help of Shannon theorem. What does Shannon theorem state? Shannon says that in order to, please listen, don't write it. Shannon stated that in order to recover the signal from the sampled signal, the sampling frequency should be greater than or equal to twice the maximum frequency component present in the system. You got my point or not? Is it not that just the signal is there, I am taking this and this part, process it, okay, give me the result? No. If you do like in arbitrary way, your signal will never be recovered. Okay, in order to recover the signal, you have to go the sampling process at a frequency greater than or equal to twice the maximum frequency component present in that signal. You got my point or not? Okay, it means for example, if the maximum frequency component is 2 megahertz, then what should be the minimum sampling frequency? 2 into 2 megahertz, that is 4 megahertz. The minimum frequency of the sampling should be 4 megahertz. It can be greater than, in order to have more better results, to recover the signal in a full form, okay, because there will be always some error in recovering the signal. It is not that, but if you will do the sampling at a frequency less than twice the maximum frequency, there will be great error. There will be great error, but there is chances the error will be minimum if the minimum frequency is greater than or equal to twice the maximum frequency component. This statement is given by Shannon and therefore known as Shannon sampling theorem. Clear? Is it clear? Very simple one-line statement is there, but a lot of numericals, tricky numericals can be asked on the basis of Shannon sampling theorem in your competitive exams. Clear? So far what we have covered, the digital control system. What is a digital control system? Okay, in fact the proper word being used is the continuous signal and discrete signal. Continuous signal and discrete signal. Basically, now this is what? Still we haven't moved to the digital. This is discrete. Discrete means separate. Discrete means something which has own its identity, while continuous means after one another. So this is basically, one is continuous and another is discrete. And then we have highlighted the advantage of the discrete control system. Okay, that discrete control system can be handled through a processor, okay, which has a high memory storage, which has a fastness in the speed, then accuracy is also there, then flexibility is also there. So these are some highlights. Then we have I have discussed about the sampler. Okay, now you will ask about the sampling, how the sampling can be accomplished or how it is being diagrammatically represented. Basically, when I say a pulse is being applied, what does this mean by pulse? Okay, so what I am doing basically, it is a switch. I will represent it by a switch. So suppose switch is closed, then signal will move continuously. Is it clear? Now if I open the switch, signal will be blocked. Again close it, again signal will arrive. Is it not? So if this switch keep on moving on and off, what I will get? I will get an sample signal. Is it not? Okay, now it depends upon how fast. Now these are not manual switch. If you take the manual switch, then it will take seconds to operate. Is it clear? For example, the 2-pole switch are present in, if you take this, switch on, just to explain you, I am showing that you can manually, if I do, how will you get? But these are electronic switch. These are electronic switch, like your BJT and all this. Is it clear? They are thyristor. Is it clear? They operate at such a speed that within a few seconds, millions of these signals can pass through it. Is it clear? So how diagrammatically a sampler is being represented? So I will show you the diagram. Side by side, we will start with the mathematics also, that what is the, because now it is no more continuous, discrete. So here you have an input, okay, here a switch is there, okay, so let the input be ft, let the input be ft, is it clear? Here a sampler is there with time t, with time t, means time is the time duration of the pulse, is it clear? So if and this is my system, so what I get an input, okay, if it is closed, the input will be passed to the system, and system will give the output, okay. It will suppose remain closed for time period t, then after what happen, it became open, what you will get? 0. After a particular time, again switch will close, signal will pass, remain closed for particular duration, then open, then ultimately you will get like this according to the waveform of the input signal. Is it clear or not? So sampling is represented by a switch, sampling is represented by switch, and this is called sampler. Now had there been impulse pulse, then I would have represented by clear, impulse means existing at a particular time, is it clear? And had there been a pulse, it would have some duration t. You got my point or not? Is it clear? So be careful in this, that what is given in your question. Now one more important thing, this is what here? ft. This is what here? ft. What is here? What is here? Now it will be a new term, it will be a new function which is known as stirred signal and represented like this, f star t. The output of a sampler is a stirred signal, S-T-A-R-R-E-D, stirred signal, and represented like f star t. I can't say that here it is ft. Mind it, ft is here, ft represent continuous signal, while star with the ft represent a sampled signal, So from wherever a sampler is there, its output will be always be a stirred signal represented by f star t. You got my point or not? Okay, so with this much of the background, now for an ordinary practical sampler, there will be always a time duration t, but generally we handle mathematically all the problem with the ideal sampler. With an ideal sampler, ideal sampler means that it exists, that we are giving what? Impulses rather than pulses. Practically there used to be always a pulses with duration time t, but ideally when we will handle the numerical problems, we will always consider an impulse sampler. We will consider an impulse sampler existing at a particular time, not for particular duration. You got my point? Okay, if it is a impulse, it will have a duration delta t, but if it is an impulse, okay, this delta t tends to 0. Is it clear? So ideally, whenever I will write down, whenever I will draw the schematic diagram of a sampler, if nothing is written, you will assume it to be an ideal sampler, that is, impulse is being applied. It closes and opens. Clear or not? Okay. Now next. Now you also know that how mathematically an impulse is represented. Delta t, mathematically it is represented by delta t, and delta t is equal to something magnitude 1 for t is equal to 0, and for other than t it is always 0. So you should keep in mind how an impulse is represented, because this will be useful in our mathematical derivation. Is it clear? Now come the sampling process. So I am drawing 3 diagrams, okay, in order to derive the mathematical form of a sampling process. Is it clear? So that you can now handle the mathematical problems related to the sampling process. And then after giving the mathematical description of sample, we will come across another transform which is known as Z transform. So far, how many transforms you have learned? First of all, Laplace transform, and then Fourier transform, and now another transform known as Z transform. Okay, it is always be Z transform, means you did not have to confuse, such should I use Z or Laplace? If it is a digital or discrete signal, you always go for Z transform. If it is a continuous signal, you have to go either for Laplace transform or Fourier transform. Is it clear or not? So first of all, before proceeding to the Z transform, okay, basically Z transform is also same way. What is the function of Laplace transform? Give me the practical form, not the mathematical form. What is the physical significance of Laplace transform? What I actually do? No, not the answer. Yes, it converts time domain into frequency domain. Z transform do the same thing, but now it do for discrete signal. Is it clear? So we make certain more mathematical we calculate basically Laplace transform only. But then we found that if we take discrete signal and find out its Laplace transform and we'll keep it as it is, then the whole integration will become very complex. So what we do, we just substitute certain value and assume that this is like this is Z, okay, so that became a Z transform, and now the things became very, very easy. So just as we have Laplace transform of standard signal, we have a Z transform of standard signals. So as we have inverse Laplace transform, we will be having a inverse Z transform also. You got my point? Okay, so what we are going to do in this, first of all, the mathematical description of a sampler, then the concept of the Laplace transform, which will be converted into Z transform, and then inverse Z transform. Clear or not? So let us move. I am drawing again we will assume the sampler to be ideal. Ideal in the sense that impulse will be applied. This is suppose any continuous signal is there, okay, extending from 0, t, 2t, 3t, 4t, this is minus t, this is minus 2t, this is minus 3t, like this. Clear? Now I am going for sampling process, and that is also in an ideal way. Ideal way means I have to apply an impulse train. I have to apply an impulse train. So I am showing here the impulse train. Clear? What I have done? Continuous signal and then a impulse train for sampling the process has been applied. So what will be the net output? Now when this is applied to this, I will get this much only. So what will be the output? Output will be also an impulse train, but of different magnitude. Here it is suppose a unit magnitude. It is of, I have applied impulse of unit magnitude, but when I apply on this, I will get an impulse train of different magnitude. Do you agree or not? Okay, so here the magnitude is suppose less, I will get a small impulse. Here it is a big one, I will get a big one. Here again a small one, a small one. Here again like this. On the similarly on this side also, here a small one, here a big one, here a small one, like this way, extending again from T, 2T, 3T like this. Clear or not? Okay. Now this is my output. This is my output. Now write down. The impulses, the unit impulses occurring at T is equal to KT, where K is equal to minus infinity to plus infinity. Mathematically represented statement. This is T minus KT. Do you agree with this mathematical expression, or I have to go or revise the circuit theory concept again? Now see, what is this? I have given a mathematical form to this impulses. What if it is a single impulse is there? How will you represent it? Delta T is equal to 1. Is it clear? For T is equal to 0 and is equal to 0 for T not equal to 0. Is it clear? This is, you agree or not? Okay. But I have a train of impulses. Train of impulses. So suppose this is delta T. Clear? This will become what? Delta T minus T. This will be delta T minus 2T. This will be delta T minus 3T. And these are all in a summation form because existing simultaneously. Therefore, can I represent it by summation K extending from minus infinity to plus infinity delta T minus KT. That is what I have represented here. Do you agree or not? Okay, what is this? FT. This is what? FT. And I am getting this sample output. What is this? F star T. Do you agree or not? Okay. So, what is my F star T in terms of this FT and delta T? Yes. Summation K is equal to minus infinity to infinity F T minus KT, T minus KT multiply by delta T minus KT. Are do you agree or not? Do you agree? Because I will be getting here the output of this only. At 2t I will getting this much output only. So I have chosen ft minus kt. Multiply by the unit impulse delta t minus kt at that particular instant. Clear or not? Okay. So this is the mathematical representation of a steered signal. It is clear or not? Okay. So with this much of the background, now this expression will be utilized in deriving the Z transform, because now we will convert. Now this is in time domain. Small t signify it is in time domain. I have to convert it into frequency domain, S domain. Okay, so I will be utilizing this expression. Okay, but what happens as soon as I will convert into this expression, the expression became complex. The expression became complex. So I will replace certain complex quantity by a variable Z, and now from now onwards, that the frequency domain of a digital sample signal will be now termed as a Z transform. Is it clear? So tomorrow we will focus on Z transform. Is it clear or not? Okay, so that's all for today.